Training state-of-the-art classical artificial intelligence requires an escalating toll in energy consumption and hardware footprint. We are approaching a hard physical limit, where scaling these classical models yields diminishing returns against massive computational friction. Quantum computing offers a theoretical exit from this bottleneck, promising computational states that can process complex, multivariable optimizations far beyond classical capabilities. But the hardware reality is strict. Large-scale, fault-tolerant quantum computers capable of running full artificial neural networks natively are still years away from commercial viability. This timeline illustrates the current operational reality. Classical AI sits plateaued on the left, while fault-tolerant quantum remains distant on the right. We are currently operating in the empty space between them, the NISQ era, or noisy intermediate-scale quantum. Waiting for perfect, error-corrected quantum hardware to arrive massive optimization and efficiency opportunities on the table right now. Organizations can bridge this technological gap today. By engineering hybrid architectures, we can fuse the trained representations of classical neural networks with the processing power of near-term quantum circuits. This is achieved through a closed-loop infrastructure stack called QSynapse. The framework operates on 5 distinct steps. It systematically converts classical weights, augments the model with quantum circuits, executes the hybrid logic, explains the resulting behavior, and optimizes the final architecture. We do not need to wait for perfect quantum computers to gain a quantum advantage in production environments. We simply require the systematic infrastructure to translate and execute hybrid models on the hardware we have today. In this GPT-2 small transformer, we isolate the classical attention heads. Instead of training a new quantum model, we use NN to QC to extract trained classical weights directly from the architecture. These are cleanly replaced with new variational quantum circuits. These specific circuits are tightly restricted to a 4 to 6 qubit footprint. That size is an absolute operational requirement for running stably within the noisy constraints of current NISQ-era processors. Despite swapping classical layers for quantum gates, the entire architecture remains fully trainable end-to-end. This continuous trainability is maintained across the hybrid divide using the parameter shift rule, a mathematical technique that calculates exact gradients for quantum circuits using classical optimization loops. By surgically replacing targeted classical components with optimized quantum logic, engineers elevate an existing large language model into a quantum-augmented transformer, fully executable on currently available hardware. Building a hybrid architecture creates an immediate engineering friction, the continuous, data-heavy handoffs back and forth between classical CPUs and quantum processing units. Executing these continuous classical to quantum circuit calls generates a severe input-output bottleneck. The sheer volume of data traffic drastically slows down inference times, threatening the practical viability of the entire model. The Quad Atlas framework clears this traffic jam by restructuring how data approaches the quantum layer. This diagram demonstrates the structural solution, sequence pooling. Instead of sending single data tokens through the quantum circuit one by one, the system systematically aggregates the tokens into unified representations before making the call. Implementing sequence pooling yields a measurable 8 times reduction in the total number of required quantum circuit calls. This massive reduction in computational overhead is executed with absolutely zero degradation in the model's accuracy. Integrating quantum processing into AI yields no advantage if data transfer chokes the system's operational speed. Sequence pooling is the specific mechanical adjustment that makes hybrid inference practically viable for real-world production. Transitioning to quantum representations introduces a primary operational risk for deployment: the deeply uninterpretable black box nature of quantum mechanics. Once classical weights translate into a quantum state, their internal decisions become entirely opaque to the engineers and compliance teams attempting to audit them. Here we see a visual representation of QSynapse. It is an explainability methodology designed to pierce that black box by isolating and quantifying the exact mathematical contribution of individual quantum dates. The system applies FQSynapse, running a Mamdani fuzzy inference system over these measured values. This fuzzy logic translates abstract quantum states into strict linguistic labels: negligible, minor, moderate, and critical. Engineers utilize these explicit labels to aggressively prune the network. they strip away the negligible gates, which reduces the overall depth and complexity of the circuit. This rigorous pruning technique maintains a 100% preservation rate of critical entanglement-creating gates across all benchmark circuits. Explainable AI serves as the precise diagnostic tool required to systematically prune and optimize quantum hardware without destroying its inherent computational advantages. Stepping back from the internal circuit view, we can evaluate how this complete, optimized hybrid model actually performs in standardized natural language processing environments. The baseline testing parameters pit the 124 million parameter Quad-Atlas hybrid model directly against a perfectly matched entirely classical GPT-2 baseline. This table charts the direct performance comparison. On the Wiki-Text-2 benchmark, the hybrid model records a 10.5% improvement over the classical baseline. That improvement is measured as a reduction in perplexity, the strict metric of a language model's uncertainty. A lower perplexity score equals a distinct improvement in intelligence and predictive accuracy. Testing the model's ability to understand complex context and long-range NLP dependencies on the Lambda benchmark yields a 30.9% reduction in perplexity. The hybrid architecture operates with nearly a third less uncertainty than the exact same model architecture running purely on classical compute. By systematically converting classical weights, managing the input bottleneck, and utilizing fuzzy logic to prune the resulting circuits, hybrid AI quantum integration operates as a deployable, auditable infrastructure layer capable of dramatically upgrading current-generation AI models today.